Welcome. We're going to do task 6.3 and we're going to try and expand the definition of trig functions beyond the right triangles here. All right. So anyway, the first thing is that from 6.2 they noticed there's a general formula that worked for the height of the Ferris wheel. H of t is equal to 30, that was the midpoint, plus 25, that's the radius, times the sine of theta. So no matter what the theta was, the calculator gave them the correct answer for the height, even though the angle exceeds 90 degrees. So there's something the calculator is doing here to compensate for this. They don't understand why, since right triangle trig only defines the sign for acute angles, and some of these angles are greater than 90 degrees. So, like for example, if you have a 60-degree angle and you found the sine of 60 degrees, the ratio of the height to the hypotenuse is going to be the square root of 3 over 2 to 1, or the square root of 3 over 2. However, if you took the angle to 40 degrees and you took the sine function, you end up with the same square root of 3 over 2, but this time it's negative. And so that it seems like that calculator is making that adjustment as to, for a particular angle, what is the height? Is it positive or is it negative? At least on the quadrant here. Carlos says sometimes the calculator gives you positives, sometimes it gives you negatives. So without looking at your calculator, what are 5 angles for which it should be positive? Well, it's quadrant 1 and 2 should be positive. So anything like 20, 50, 100, 175, 179 degrees. So really anything in 0 to 180 degrees, whereas the negative is anything in quadrant 3 and quadrant 4. So this would be 181, 182, 200, 260, and 359 degrees would be some possibilities. But then Clarita says, yeah, and sometimes we can't even draw the triangle. Remember, this right triangle trig was based on the ratio of a right triangle, the ratio of sides on a right triangle. We can't even draw it, but it still gives us angles of rotation. So for example, 180 degrees. Well, if it's extending to 180 degrees, we can't drop a vertical or horizontal line here because it is horizontal. And so what's interesting is if you look at what is the sine of 180, it's able to work with that even though that's not a right triangle. And it'll give you a 0 for that. Some others might be 0, 90, 180, 270, 360. So something's going on here. And Carlos says because of the symmetry, some angles of rotation should have the same values for the sine. So as an example, let's say you have a 60-degree angle, right? Well, that's going to have the same ratio as this will be 180 minus 60, or 120 degrees. So we can say that the sine of 60 equals the sine of 120 degrees. Same thing would be true if we used the symmetry for quadrant 3 and quadrant 4. Those would be negative values, but they would be, if this triangle right here, which is the reference triangle, is the same as this triangle, which is also a reference triangle, then we can say that their sine values are the same. And how big and how small? Well, actually, certainly anything with 360 degrees, but we've seen, whoa, how about that? We've seen that it can be greater than 360 degrees, so it can rotate over. In fact, it can continue that infinitely. In fact, It could even be less than 0. You can also represent it as a negative degree. So therefore, I would have to say that it is anything, all the real numbers here, negative infinity to infinity. Okay, and then Clarita says, well, whatever the calculator is doing, at least it's consistent with our right triangle definition of sine as the ratio of the length opposite to the length of the hypotenuse. And that comes back to the idea of these reference triangles that you can draw. Okay, so this triangle right here, and this triangle right here, those are congruent triangles. All right, and that's called a reference triangle, and that's what it